Okay, welcome back everyone. We have a couple of minutes before class officially starts. I'm glad that I started a little bit early because just as I was setting up the live stream, I realized that I had not actually scheduled it yet. So you were probably, if you're here now, you were probably at the course webpage waiting for this thing to show up. So I just did that now. So, a couple of questions, or a question here. In a rootish array stack, are the last two rows always wasted space, or just the empty spots? The last two rows are not always wasted. Sometimes those last two rows are full. So, if you just keep adding and you happen to hit a number of elements which is exactly of the form r times r plus 1 over 2, so then the number of elements you have is of that form, then you'll have a perfectly filled thing and the last two rows won't be wasted space. But that doesn't mean that there's no wasted space, because remember, there's still, beside all of those rows, there's a list that keeps track of pointers to each of those rows, and there's about the square root n of those rows, so there's still square root n wasted space, even if all the rows are perfectly filled. Is that psi inside the sigma for the first equation? No, it's little x. So it looks like the usual sort of lag or latency, somewhere around 15 to 20 seconds from the time I speak until the time I see it, at least on this iPad. Okay, so as promised last class when we studied skip lists, and we studied how they work, both as sorted sets and how they work as list implementations. And basically, you after that class, you know enough, maybe consulting a book, to go ahead and implement skip lists. They're not that complicated to implement. But we had left off this sort of important theorem about skip lists, which was to do with the expected length of the search path. And really, everything relies on that theorem. It's important that the search path for any particular element is short, because that every algorithm on skip lists follows the search path for some element. So that's what we'll prove today. So just leading up to that, let's just remember what a skip list was. You imagine that you start with a base list L0 that contains n elements, and then you repeatedly take a what's called a Bernoulli sample from that list. That means you toss a coin for each element in the list. If the coin comes up heads, it moves up into the next list, and then you repeat that on the subsequent lists until you have nothing left. Okay, so here I end up starting with n elements in L0, then I get a non-empty L1, a non-empty L2, a non-empty L3, and I guess implicitly L4 was empty. So when I tossed the last coin to decide if this was going to get promoted into L4, it came up tails, so it's not there. And even though L4 is not there, or it's empty, we can still imagine that it exists. In particular, it'll be helpful for us to imagine that actually a skip list is an infinite number of lists, L0, L1, L2, L3, L4, and so on, all the way to infinity. It's just that some of those lists happen to be empty. All right. Now, since these things are randomized, we need a little bit of probability to study them. And I will not carefully or formally define things too much here, because that's the subject of other courses, and there's no point in doing it twice. So I'll just quickly introduce you to the important things about random variables for us. If you've taken 2804, you've seen these, and if you're taking 2804, you'll see them soon. But for now, we can jump ahead and still get the main point across. So a random variable, the way we'll think of it is it's a real number that takes on different values with different probabilities. So for example, one possible random variable is a random bit, which takes on the value 0 with probability 1/2 and takes on the value 1 with probability 1/2. So that's an example of a random variable. Maybe more familiar to you is a six-sided die. So when you roll a six-sided die, it lands on one of its six sides, and one of its six sides is facing up, and there's a number printed on there, or there's a number of dots on there that's 1, 2, 3, 4, 5, or 6. And you can imagine then that, well, that thing, when you roll it and you look at the number there, that's a random variable. So it's a number that comes up, and it comes up with different values with certain probabilities. Okay. So for example, well, I'll just write that down. So random bit with a random bit, the probability of a 0 is the same as the probability of 1 is 1/2. And with the six-sided die, the probability of 1 is the same as the probability of 2, is the same as the probability of 3, and so on all the way up to 6. So each of those 6 numbers is equally likely. Each one has probability 1/6. And for random bits, you get this. So this is a six-sided die. And this is the random variable you would get from a random bit. And one of the main things we want to study about random variables is their expected value, which is just defined as you take the sum over all the possible values that the variable could take, and you take that value and you multiply it by the probability that the thing actually comes up with that value. So this is kind of like an average. It's called expected value because it's what you would expect to get if you did this experiment, you did whatever the underlying experiment is a whole bunch of times and then took the average. Okay. So for example, if we apply this formula to a random bit, then we get that the expected value of this random bit, we have to take a sum over all the possible values that the bit can take on. Well, there's two values. There's a 0 and a 1. So we have to take 0 times the probability that the bit equals 0, and plus 1 times the probability that the bit equals 1. And this is 0 times 1/2 plus 1 times 1/2, which is just 1/2. So the expected value of a random bit is 1/2. That's just according to this definition. And you can imagine if you took a whole bunch of random bits, n of them, added them up and then divided by n, you'd kind of expect something close to 1/2 there. So important thing to note is the expected value does not have to be an actual value that this random variable can take on. So the expected value of a random bit is 1/2, even though it can never take on the value 1/2. Right? It's either 0 or it's 1, but still somehow on average it's 1/2. And for the six-sided die, what's the expected value of that thing? well, there you have to add up. So expected value of 6-sided die, you're going to have a sum with 6 terms, and each one is multiplied by 1 over 6, so it's going to look like 1 times 1 over 6 plus 2 times 1 over 6 plus 3 times 1 over 6 all the way up to 6 times 1 over 6. And if you add all of that up, it's 3.5. So this is a useful thing to know if you play any kind of board games. If you gamble with dice, this is a pretty basic and important fact, that on average when you roll a 6-sided die, the number that comes up is 3.5. So again, another example where the expected value is not actually something that ever happens, but it's if you averaged over many trials, you would get this number. All right. So this is the definition of expected value. And here's the most important thing, the most useful thing about expected value. This property that I'll explain in a second is called linearity of expectation. Okay. So it says that the expected value of 2 random variables, x and y, if I add them together, so I take their sum, then the way to get the expected value of that thing is just to take the sum of the 2 expected values. This is extremely useful because on the left-hand side is what is often a complicated thing that we can break up into simpler parts that are easier to understand. And there's a extreme version of this where actually what we have is a sum of many random variables. Then we would like to know the expected value of that sum. Well, it turns out that that's just the sum of the expected values. Okay. And we will see already today some examples where we have a very complicated looking random variable here on the left-hand side, and we're able to express it as the sum of very simple things on the right-hand side. So it's the sum of very simple things, so simple that we can easily compute their expected value. In fact, we can compute them with little computations like this, 2 terms sometimes. All right. Okay. So let's just remember those 2 things. This is the definition of expected value, and this is the most useful property. It's called linearity of expectation. So let's start with a basic experiment, which is the following. So I say, how many times, well, let's say x, we'll give it a name, it's a random variable, is equal to the number of times we toss a coin until it comes up heads. So imagine we do this experiment. We toss a coin. If it comes up tails, we toss it again. We keep doing that until the first time it comes up heads, and then we stop. And now the number of those coin tosses, so that's going to be an integer. And it's a sort of random integer because if we do this experiment different times, we get different numbers, and we'll see that we get various numbers with various probabilities. So that means we really have that that number of coin tosses until we get the first head is a random variable. So we can ask about its expected value. They have to be independent events, right? So that's a question. Do they have to be independent events? Well, first, we're not talking about events here. We're talking about random variables. But this is the incredible thing about linearity of expectation, or what's so useful about it, is it does not require any assumptions about the random variables. So it doesn't require that they be independent. So they can be very much related, and this is still true. Okay, so let's think about this. I want to toss a coin until it comes up heads, count the number of times. That's my random variable x. So for example, sometimes I get, if I do this experiment, the first thing that happens is I get a head, and when that happens, then x equals 1. Or maybe I get a tails and then a head, and when that happens, x equals 2. Or maybe I get a tails, tails, heads, and when that happens, x equals 3. And so on. Okay. So there's a couple of ways we can do this, and I want to use a way that will help us in the future for what we're going to do next. But first of all, let's think about, why am I talking about this? Well, tossing coins is pretty relevant to what we're doing now, right? We're studying skip lists. Skip lists are built on coin tosses, and in fact there are elements of a skip list, certain parts of it, that you can exactly describe as the number of times you toss a coin until the first time it comes up heads, or equivalently until the first time it comes up tails. Let's think about this for a minute, and I'm going to use linearity of expectation to make this problem easier. And here's what I'll do. I'll say for each integer I bigger than or equal to 1, we'll just define this variable xi, which is either going to be equal to 1 or 0. So it's going to be like a random bit, but maybe not evenly distributed. And it's going to be 1 if we have to make the ith coin toss. And it's 0 otherwise. Okay. So what does this mean? When do we have to make the ith coin toss? Well, this is the first coin toss. This one here would be the second coin toss. This one here would be the third coin toss. When do we have to make that ith coin toss? Well, we have to make it when the previous I minus 1 coin tosses all came up tails. Okay. All right. So for example, if this is my outcome, if I toss the coin and the first time I toss it, it comes up heads, then I will get x1 is equal to 1, because I always have to toss the first coin. But then x2 is equal to 0, x3 is equal to 0, and so on. All the other xi's are equal to 0. In a case like this, I would have x1 equals 1, x2 equals 1, x3 equals 1, and then x4 onward, they're all equal to 0. Because I didn't have to toss the coin a 4th time, I didn't have to toss it a 5th time, I didn't have to toss it a 6th time. all right? And here's the nice thing about this, about writing it this way, is x, which is the number of times that I toss a coin until it comes up heads, it's just equal to the sum I equals 1 to infinity of xi. Just the way I've defined things, right? Basically, you write down the sequence of coin tosses, you're counting a 1 each time you toss it, and then afterwards, once you've done the last coin toss because it came up heads, then you just write down an infinite sequence of zeros. Well, the number of 1s you wrote down is, of course, the number of coin tosses you made. That's all that this says. Okay? So that's good. Now, if x is equal to the sum of these things, well, that just means that the expected value of x, I mean, there's nothing strange. I mean, x equals this means the expected value of x equals the expected value of this, right? That's nothing weird there. But now this thing is a sum, and it's an expected value of a sum. And I've already said that the most important thing about expected values is that the expected value of a sum is the sum of the expected values. So let's go ahead and use that. So I can take the sum out. And so what I need to do now is figure out the expected value of x sub I. Okay. So for that, we can now use the definition, because x sub I is so simple, it's only 1 or 0. We can just write out the expected value longhand, right? So the expected value of x sub I is equal to 0 times the probability that x sub I is equal to 0 plus 1 times the probability that x sub I is equal to 1. So there's two probabilities we want to know, but actually one of them we don't care about because we're just going to multiply it by 0 anyway. So really this is just 1 times the probability that x sub I equals 1, which is just the probability that x sub I equals 1. And what's the definition of x sub I? X sub I is 1 if we had to make the ith coin toss. And we already said, when does that happen? That happens when the first I minus 1 coin tosses all come up tails. So that's just the probability that the first I minus 1 coins come up tails. So now I think this is something we all have a good intuition on. If I toss a coin 3 times, what's the probability that it comes up tails all 3 times? Well, this is where this question was asked about independence. This is where independence comes in, but the probability that it comes up tails the first time is 1/2. The probability that it comes up tails the second time is 1/2, and the probability that it comes up tails the third time is 1/2. And those 3 events are independent, which means that it's just so the probability that we get 3 coin tosses in a row that are all tails is 1/2 to the power 3, and the probability that we get I minus 1 coin tosses in a row that are all tails is 1/2 to the I minus 1. Okay. So now we've computed the value of x sub I, expected value of x sub I. It's 1 over 2 to the I minus 1. So we can plug that in here. This is equal to the sum I equals 1 to infinity of 1 over 2 to the I minus 1. So if we write that out longhand, well, when I equals 1, this is 1 over 2 to the 0. So that's 1 over 1. When I equals 2, this is 1 over 2 to the 1, so it's 1/2. When I equals 3, it's 1 over 2 squared. 2 squared is 4, so it's 1/4. And when I equals 4, it's 1/8, 1/16, 1/32, and so on. And this sum, you may or may not know it. Let's just reason through it and see where it what it evaluates to. Best way to think of it, because it lets you remember it, and I like, rather than just memorizing formulas for things, I prefer to understand and have an explanation of why they're so. And so this is one that goes back to, well, it goes back longer than that, but it was, there's a nice story about it. Zeno of Elea was, I guess, a Greek philosopher who used to make up these, he called them paradoxes. So things that seem to be self-contradictory or that you couldn't explain. And Zeno's paradox, one of them at least, and the one that he's most famous for, is about running a marathon, because Greeks, ancient Greeks, love to run marathons, I guess. And the paradox, which is not really a paradox, but is confusing if you think about it for a little while, says that, well, if I want to run a marathon, before I can run the entire marathon, I first have to run a half marathon. Right? I have to run halfway. And once I've run the halfway, then I still have a half marathon to go. And before I can finish that, I still have to do a quarter marathon. But once I've done that, I still have a quarter marathon to go. And before I finish that, I still have to do 1/8 of a marathon. And so the paradox was, well, then you can never run a marathon because there's like this infinite number of steps that you have to take. And each time you take a step, you're still not there. You're only halfway. You're only halfway there from where you were in the previous step. How does that apply here? Well, here you think of a marathon as something whose length is 2. And here's the first step that you take. It's a step of length 1. And then the next, so what's left is still something of length 1. And the next step that you take is of length 1/2. But what's left is still exactly something of length 1/2. And the next step is of length 1/4. And you're left with a quarter. And the next step is 1/8. And you're left with 1/8. And then a 16th. And a 32nd. And a 64th. And so on. And you never quite get to 2. So you get closer and closer to 2, but you never quite get there, and it's only in the limit that this sum actually makes it to 2. So this thing is equal to 2. So the expected value of x, which is the number of coin tosses until we see a heads, is 2. Now, if we had just guessed before we started, what did we think the average number of coin tosses would be before you saw heads? You probably would have guessed 2. But our guesses can be wrong here, especially with probability. Sometimes our intuition is very misleading, but in this case it's correct. So the answer is 2. All right. Good. And what does that have to do with skip lists? Well, for one thing, it tells us if we just take a particular element and in list 0 and say, well, what's the expected number of lists that that element participates in? Well, the number of lists it participates in is exactly given by the number of coin tosses that come up, in this case, they come up tails, or come up heads before the first time they come up tails. So on average, you will see an element in 2 lists. One of those lists is L0. They're all in L0, and then one more list on average beyond that. Okay, good. Let's so in a skip list now, let's say for each I in each integer I bigger than or equal to 0, we use this to denote this just equals the size of Li. And that's not including the sentinel. So in this case, the size of L0 is 1, 2, 3, 4, 5, 6, 7, 8. The size of L1 is 1, 2, 3, 4. The size of L2 is 2, and the size of L3 is 1. And so I think it's probably believed that it's important, well, if we want to show that a skip list is efficient, we should certainly be able to show that it's not too big. So we should look at the expected size of the skip list by adding up the sizes of all of the lists, L0, L1, L2, L3, and so on. And for now, we'll skip the sentinel. We'll see how to deal with the sentinel soon. So let's, if we look at the sum, I equals 0. And again, we have to take this sum all the way to infinity because it's always possible that some element just, you know, for any number k, it's possible that some element rises all the way up to level k. All that takes is k minus 1 tails in a row when you're tossing coins for that thing. So we take this I equals 0 to infinity. The size of Li, that's the size of the list. Yeah, so we want to know that thing, the expected value of that thing because it's a random variable. And right away, if we have an expected value of a sum, we should look at the sum of the expected values. They're almost always easier to figure out these things because they're simpler. And so what is the expected size of Li? Well, we know, I mean, we've seen a strategy for how to get these things. Let's just define a bunch of these really simple variables like we did for the coin tossing, because it's almost the same problem. And so just to make life easy for us, let's pretend that the things that are in the list L0, the values that are there, are just the integers 1, 2, 3 up to n. just so we have names for them. So we'll just say xij is going to be equal to 1 if j is in list I and 0 otherwise. And that's for j being any of those integers 1 through n that show up in the bottom list, because those are the only ones that can show up in the upper lists. Okay. So now, Li, or the size of Li, how can I figure out its size in terms of these things? Well, each of these things tells me whether or not j is in list I. So to get the size of Li, I can just sum over all of those things. So for example, in this case, x11 is equal to 1 because the element 1 is in list 1. x12 is equal to 0 because 2 is not in list 1. x13 is equal to 1 because 3 is in list 1, but x14 is 0, x15 is 0, x16 is 1, x17 is 1, and x1n is 0 because this one is not in list 1. So that just, all that just to say then that the size of this list Li is just the sum j equals 1 through n of xij, which means that the expected size of that list is the expected value of the sum. And if we have an expected value of a sum, we should always take the sum of expected values. Equals 1 up to n. So now I'm down to a really simple thing. I need to know the expected value of xij. Xij is one of these really simple variables that's only 0, it's only 0 or 1. So that means when we try and compute its expected value, it's going to be this simple thing. The probability that it's equal to 0 doesn't matter because we're just going to multiply that by 0. The only thing that matters is the probability that it's equal to 1. And so this thing here is the sum j equals 1 to n of the probability that xij is equal to 1. But wait a minute. When is xij equal to 1? So pick your j in the bottom list, and you're just asking what's the probability that j makes it all the way up to list I. Well, that happens if there are if there are I coin tosses which come up heads, right? If I want to make it into list 1, then I need the first coin toss to come up heads. If I want to make it into list 2, then I need 2 coin tosses to come up heads. If I want to make it to list 3, then I need 3 coin tosses to come up heads. So this probability that xij is equal to 1 is just the probability that I toss a coin I times and it comes up heads every single time. And that is just 1 over 2 to the I. We've seen that. So this is the sum, j equals 1 to n of 1 over 2 to the I. So this is just 1 over 2 to the I plus 1 over 2 to the I plus 1 over 2 to the I, that many times, n times. So this is just n over 2 to the I. So expected size of Li is n over 2 to the I. We can put that in here. This is equal to the sum I is equal to 0 to infinity of n over 2 to the I. We can take the n in front of that sum. And this sum I equals 0 to infinity of 1 over 2 to the I, we've seen it. This is 1 plus 1/2 plus 1/4 plus 1/8 and so on. So this sum here, the whole thing only adds up to 2 when we multiply it by n, so we get 2n. Okay, so if I ask what's the expected size of this whole skip list, all the lists in there, but not counting the sentinel, then the answer is 2n. So maybe not, in fact, not surprising at all, given what we had done just before that. So basically, on average, this thing is stores each, you can think of it as, on average, it stores each item twice, or it uses twice as many nodes as show up in the bottom list. Shouldn't it be from I equals 1 to n and not j? No. I is the list index, so it starts at 0 and goes up to infinity. And j counts from 1 to n, because these are the numbers of the things in the lower list. Is there somewhere that I wrote I equals j to something? I don't think so. Anyway, okay, good. So let's keep track of these things that we've been showing here. Well, we showed this, that the total size is, expected size is 2n, but on the way we showed this important thing, that the expected size of Li, let's remember it, expected size of Li, this will be important, is equal to 2n. All right, so now we get to something a little bit trickier. And what is that? Well, we've been counting the size, ignoring the sentinel. But the sentinel is there, and we need to actually make nodes for this thing, or at least make one pointer for each of these things. And so what that really means is we also would like to know the height of this thing, right? So the height that's equal to the maximum value I such that Li is not empty. Right? So the height of this one is 3 because L3 is not empty. There's something in it. But L4 is empty. There's nothing in list L4. So, so we call that the height of the skip list. And of course, the height is a random variable. It depends on the coin tosses. So it's a random variable, and we can ask for its expected value. Okay. And that's going to be the expected value of this thing. But actually, so we have a nice linearity of expectation that we get to use for sums, but the expected value of a max, there's no nice formula for that. There's no nothing simple like this where the expected value of a max is, I mean, there's just no way to easily break this down. We need to do something more clever. And we're going to follow the same strategy that we used when we were studying the first basic problem we studied, which was how many coin tosses you have to do until the first head. Okay. So we're going to say, define I sub I is 0 or 1, and it's 0 if L sub I is empty, and it's 1 otherwise. Okay. And that's for I bigger than or equal to 0. Now we have another way to write the height. The height is just the sum I equals 0 to infinity of I sub I. Right? So we have this thing that is 1 if, no, it's even better than that. Let's say I plus 1 here. Yeah, so I think it makes sense to say height is the number of lists that we have, because then it's the number of sentinels, right? So if L sub I, so L sub 3 is non-empty, that means we have 4 occurrences of the sentinel. So we'll count that as 4 because L3 is not empty. Okay. All right, so we define things same way. And now you get that, well, the height is just the sum of these I sub i's, right? Because in this picture, for example, you have I sub 0 equals 1, I sub 1 equals 1, I sub 2 equals 1, I sub 3 equals 1, but then after that, I sub 4 and onwards, they're all 0, because the lists L4, L5, L6, and so on, they're all empty, so those are all 0. Okay. Why is the expected value of Li equals 2n when the size decreases after each time we go up? No, the expected, the expected sum of the sizes is 2n. This is n over 2 to the I. The 2n is this thing. So the size of expected size of Li is n over 2 to the I, and this total size is 2n. Okay. All right. So now we can write the height as the sum of these I sub i's. Let's start that here. The expected height is the expected sum I equals 0 to infinity of I sub I. We have expected value of a sum, so we use linearity of expectation. I equals 0 to infinity of the expected value of I sub I. And that means, well, we should try and figure out the expected value of I sub I. And it turns out that that's not completely trivial anymore. But we can we can figure out a way to get a bound that's almost exactly right, but it's not trivial. So when is I sub I, let's just start it and see when we get stuck. Expected value of I sub I, well, that we know is 0 times the probability that it's equal to 0 plus 1 times the probability that it's equal to 1. That just becomes the probability that I sub I is equal to 1. Okay. So here are two things that I can, and I don't know. What's this probability that I sub I equals 1? I mean, I have here 8 elements. Well, that one I could figure out that the probability that I sub 1 is equal to, well, actually, I don't even know the probability that I sub 1 is, I could figure out the probability that I sub 1 is equal to 1, but that already requires some sort of non-trivial use of a complement rule, and definitely I sub 2 I would struggle with. So let's instead think about some trivial things. Well, here's something that I know. I sub I is either 0 or 1. So that definitely means that it's less than or equal to 1. That's a sort of obvious thing. I sub I is less than or equal to 1. So if it's always less than or equal to 1, that means its expected value or its average value is also less than or equal to 1. Okay, so that's a very trivial thing. Here's something that is as trivial. So I sub I it is 1 if L sub I is not empty, and it's 0 if L sub I is empty. So that means that I sub I is also less than or equal to the size of L sub I. Let's think about that for a second. If I sub I is 0, that's because L sub I is 0, because list I is empty. If I sub I is 1, that's because list I is not empty, which means that the size of list I is either 1, 2, 3, 4, 5, or whatever, but definitely bigger than or equal to 1. So that's also a trivial thing, except that it actually tells us something about the expected value of I sub I. It tells us something that's not completely trivial. Well, if I sub I is less than the size of L sub I, then the expected value of I sub I is less than the expected value of the size of L sub I. And we actually know something. We know the expected size of L sub I. That's n over 2 to the I. Especially useful since I was corrected that I copied the wrong thing down here. But n over 2 to the I is important. So that may not sound like much, right? This thing here is smaller than 1. This thing has an n in it. But for large values of I, this thing on the right can be smaller than 1. So that's not completely trivial. Okay. And so now we can finish. We have two bounds on the expected value of I sub I. It's not bigger than 1, and it's not bigger than n over 2 to the I. So let's take this sum. This is a sum that goes from 0 to infinity, and we'll split it into two parts. One part where this is the right thing to use, and another part where this is the right thing to use. So that is just, we start with the first part, I equals 0, and we go up to the floor of log n. And, I'll put this in here. So for that first part, for those values of I, I'll just use this. The expected value of I sub I is less than or equal to 1. So that's just a smallish part. It's a sort of finite part. And then there's the infinite part, which is now I have to count from log n plus 1 all the way up to infinity. And there, I will use this inequality that says the expected value of I sub I is not more than n over 2 to the I. Okay. All right, so this thing here has log n plus 1 terms. At most log n plus 1 terms, right? It counts from 0 up to the floor of log n. If log n happens to be an integer, it will have log n plus 1 terms. Otherwise, it'll have a bit less, but certainly not more than log n plus 1. So that's where this comes from. And then this thing here, let's take a look at that thing. This first index is the floor of log n plus 1. Okay? So that means that thing is actually bigger than log n. Okay? So the first, where we start counting is at a number that's bigger than log n. And then we keep counting up here. So if I write this if I write this out longhand, I will see that this is a sum that starts out, it's first when I is bigger than log n, this is less than or equal to n, right? N over 1. 2 to the I is bigger than 1, so this is less than n over 1. But then the next term is less than n over 2. Sorry, no. This, let me pause here. This thing here, 2 to the I, is bigger than n for I bigger than log n. Okay? Because 2 to the I equals n when I equals log n. Okay? So the first term here is smaller than n over n. Okay? So that's when I equals log n plus 1. The second term is half of that. So this is smaller than n over 2n. The next term is smaller than n over 4n. The next one is smaller than n over 8n, and so on, all the way off to infinity. But wait a minute, we have all these n over n's, those cancel each other out. So this other part is just 1 plus 1/2 plus 1/4 plus 1/8, and this is 0 again. So this whole thing adds up to less than 2, which means the whole sum is log n plus 1 plus something that's less than or equal to 2. Okay. And this is non-trivial. Okay. So to get that the expected height is less than or equal to log n, that's something. That's saying something. So let's write that down. The expected height, we weren't that careful. We managed to prove that it's less than or equal to log n plus 3. Okay. Good. Now, that's an important step for us because remember, the whole point of the lecture today is to try and show that the length of the search path is 2 log n plus something. And the search path, remember, starts up here at the highest occurrence of the sentinel, and then it does some kind of walk until it falls out of the bottom list here. So in particular, the search path takes 2 kinds of steps. There's steps down and steps to the right. And the number of steps down, well, that's the height, right? The number of times we have to go down is, well, we have to go down from here, from here, from here, and then from here. That's 4 times. It's exactly the height. So we're kind of half done. So try not to get too stuck with sort of the algebra or the math here. The point is sort of the moral of this, at least, is, well, if we want to know the height, we just express it as by adding up a bunch of 1s and 0s, where it's 1 if the list is empty and 0 if it's not, or if it's 1 if the list has something in it and 0 if it's empty. And for the first log n levels, well, there's probably something in every one of those log n lists. That's what this first part of the sum is. So probably there's something there, so we might as well just give up and say, yeah, that thing is probably there. We'll just count it as being there, even if it's not. But once we get past level log n, then actually the size of the list, the expected size of the list, is smaller than 1, which seems to suggest that, well, then it's more likely that the list is, I mean, if its average size is smaller than 1, that means that it can't be there all the time, right? And, you know, as you get higher and higher up, the expected size is not just smaller than 1, but it's smaller than a half, smaller than a quarter, and so on. So right at around log n, the expected size becomes 1, and then it just becomes more and more likely just to be empty. Why n over n, n over 2n, and so on? Well, because when you get to log n, so right, this thing here starts, let's forget about the floor for a second. This thing here starts at n over, the first term is n over 2 to the log n. Let's make this really simple. What's n over 2 to the log n? That's n over n. Okay. What's the next term? It's n over 2 to the log n plus 1. What's that? Well, 2 to the log n is, well, let's do it really slowly. This is n over 2 to the log n times 2. Well, that's n. This is n again, so n over 2n. And then the next one, instead of a plus 2 here, instead of a plus 1 here, it's a plus 2. So you get n over, this becomes a 4, and then this is a 3, this becomes an 8, and so on. Okay. All right. So I want to get to the really cool part of this analysis, I mean, already this is a nice way to see how to break a sum into, use basically two trivial bounds. One is this and the other one is this to get something really non-trivial. The other is an interesting analysis technique that some people call backwards analysis. And it's to analyze the length of this list here. Okay? So now the length of this search path. So let's say the length of the search path is equal to the number of steps down plus the number of steps to the right. So if I want to know how long this path is, I count the number of steps down that it takes, and I count the number of steps to the right that it takes. Why did we want to do that? Well, because we already know the number of steps down. So that means that the expected length of the search path is the expected value of these two things, which I can use linearity of expectation. Gives me that. This one, the number of steps down, I know. It's just the height of the skip list. Okay? So this is just equal to the expected height. I know that that's not more than log n plus 3. But I'm still stuck trying to understand number of steps to the right. And for that, I'll imagine, I'll define the search path a different way. So remember this search path here, which stops at 5, it's the search path for 6. So let's think of defining it a different way. So to get the search path for 6, or to get the reverse of it, I will start down here just before 6, so at the node where the search path ends, and I'm going to walk it backwards. And the rule for that is actually really easy. So from here, if I want to follow the search path backwards, I take the greedy strategy of always trying to climb up. If I can climb up, I will. If I can't, then I'll go left. So here, 5 does not appear in the list above, so I have to go left. 4 doesn't appear in the list above, so I have to go left. 3 does appear in the list above, so I follow it up. 3 appears again up here, so I follow it up. But 3 doesn't appear up here, so I have to go left. And then finally the sentinel shows up here, and I have to go up. Okay. So that's another way to define the search path, and it gives you the same search path just in reverse. So why would I want to do that? Well, because it gives rise to a useful thought experiment. So imagine you're this person who is trying to follow this reverse search path. You don't have a picture of the skip list yet. Like, you don't have this nice picture that I have on the board. You just know that you've been following a path for a while, and maybe you've gone up some layers, and the last thing that you did was you took a step up. Okay? So now you're in level I. You just arrived here. You don't know anything about it yet. Just showed up. And now you're trying to understand, how much time am I going to spend in level I? So how much time am I going to spend walking left here? So if I don't know anything about level I, then, well, that means that my first step could be to the left, or maybe my first step is straight up. Those are the two options. I just arrived here. Maybe I'll have to go left. maybe I'll have to go up. When do I get to go up right away? Well, I get to go up right away if this node appears in level I plus 1, in list I plus 1. Okay. So think about that for a second. What decides whether this node appears up in level I plus 1? Well, that was decided at some point by a coin toss. Okay. And if the coin came up heads, then this thing shows up there. And if that happened, then you get to go up right away. You don't have to spend any more time at level I. And if the coin comes up tails, this does not go up there, and you have to spend more time at level I. But wait a minute, this sounds familiar, because that means the time that you spend, the number of nodes that you're going to see at level I before you go up, well, that's determined by one of these experiments. It's the first experiment we studied. Right? This node here, if it comes up heads, I get to go up right away. If it comes up tails, then I have to go left. And now do I get to go up, or do I have to go left? Well, that depends on what happened with the coin toss when I tossed the coin for this node to decide if it goes up or it goes left. If it came up tails, then I'll have to go left again. And when will I finally get to go up? I'll finally get to go up when I reach one of these nodes whose coin tosses came up heads. But that's exactly the experiment we were looking at. And that's the first thing we counted. How many times do I have to toss a coin before it comes up heads? That's how many nodes you will visit at this level. Okay. And the number of steps that you'll take at this level, so steps to the left, is one less than that. Okay. So let's write this down a little bit more carefully. Or what we just argued is that the expected number of steps to the, well, if you're going backwards, there's steps to the left. If you're going forwards, there's steps to the right. Let's say to the right, or horizontal steps. In Li, that's less than or equal to the expected number of coin tosses before the first head. Right? So here I have to take 2 steps because the first coin toss was tails, second coin toss was tails, then finally I got a head. So no more steps to the left here. Okay. But that's something we analyzed at the beginning. If we count the head, then that number is 2. But here we're not even counting the final head, so that number is just 1. So here I mean really before not counting the head itself. Because the head is a step up, and we're counting the steps up, and the steps to the right or left separately. All right, so now we can finish up, and this is true for any Li, right? There was nothing special about which list we happen to be in here. You just imagine you show up in the list, and now you want to know how far you have to walk to the left before you can go up. That expected number is 1. All right, so this is expected value of the height plus, so steps to the right, there's some at each of the levels, so I need to count them across all the levels. So I take the sum. Well, what are the level numbers? Well, the level numbers go from 0 all the way up to infinity of number steps right in Li. Now, again, this looks like we have a problem, but we've seen how to tackle it. There's a reason we tackled the height first, because it shows us how to deal with this. So we have a sum I equals 0 to infinity, which counts the number of steps that we'll take to the right in list I, or if we're going down, to the left if we're going backwards. But right now the only bound we have is 1. That's what we showed with these coin tosses. But there's another bound, which is the number of steps that I can take in Li to the left is not more than the number of nodes in Li. So it's not more than the size of Li. So also, this is also less than or equal to the size of Li, or the expected size of Li, which we know is less than n over 2 to the I. So this thing, we're going to do exactly the same trick again. You get expected height plus 2 sums. One of them counts from 0 to log n. For that one, we use the fact that the expected number of steps you take in Li is at most 1. And then once we get past log n, we use this thing, that the number of steps you take in the list, Li, is not more than the number of nodes in Li, not more than the size of Li. And that's exactly the same calculation again. So we can, this one here is at most log n plus 1. This one here is at most 2. And so we get, and this one here we figured out already was log n plus 3. So in total, we get less than or equal to 2 times log n, there's the 2 log n's, plus 6. And so that is the theorem that we needed. I mean, it was somehow the only difficult thing about skip lists is this theorem that tells us the expected length of the search path for X in a skip list with n nodes in L0 is at most 2 log n plus 6. Okay. So that's the only thing that we needed last class to show that all of those operations were efficient, that they ran in order log n time, and it's non-trivial, but there it is. Okay. And what does this mean practically speaking? Well, one nice thing here is we actually get real constants, 2 log n plus 6. So I can tell you these values, right? So when n is 1,000,000, this number is about 46. So you put 1,000,000 nodes items in a skip list and you try and access something, you'll have to go through about 46 things to get to it. Okay. So 46 is a tiny number for a computer to do, so things happen in accessing any item in a skip list with 1 million elements happens in a tiny fraction of a second. If you go up to 1 billion, so 1 billion you like to think of as, you know, it's about the number of operations a computer can do in a second. So in something like an array list, or an array list, if you try and modify it at position I, for example, it's going to take about a second if you have a list of length 1 billion. And in a linked list, if you try and access it at position I, it's going to take about a second if you have a list of length 1 billion. On the other hand, 2 log n plus 6, when n is 1 billion, is only about 66. Okay. So where these other things do on the order of 1 billion operations, you do about 66 operations if you use a skip list. So the math is, to prove this gets, you know, a little bit involved. And some of that is, well, because it's, you guys don't necessarily have the background yet, but that's coming. But in the end, what you get is a structure that's really simple, really fast, and it's really just a sort of a perfect general purpose thing. Okay, so I'll stop there. Does anybody have any questions? So here's one. Why from 0 to log n and then log n to infinity? Because we have 2 bounds on the expected number of steps right in list I. One of the bounds was by this coin tossing argument that says the expected number is not more than 1, because if I think of walking backwards in the list, basically I stand at a node, that node tossed a coin. If it came up heads, I get to leave right away. If it came up tails, I have to take a step, right? So then the number of steps that I take is exactly equal to the number of tails, and then the expected number is 1. And the other bound that I have is, well, maybe that's not so great. When I get up to large values of I, well, the size of the list, the expected size of the list is this, n over 2 to the I. And when I is bigger than log n, this is smaller than 1. Okay. And I certainly can't take more steps in the list than the size of the list. Otherwise, I reach the sentinel and then I have to go up. And so, so why do you split the sum? Well, you split the sum precisely at log n because at this point, 1 is smaller than n over, in this part, 1 is smaller than n over 2 to the I, so you use that. At this part, 1 is bigger than n over 2 to the I, so this is the right inequality to use. During the midterm, will there be a proctor contacting us through Zoom like that described in the course page? It turns out that probably not. It's just turning into a giant hassle for a whole bunch of reasons to do this. What you should do, and there'll be some announcements about this, is during the scheduled time for this exam, and that includes even if you have special accommodations for it, the exam will open on the course webpage, so on the CU Learn webpage. You'll go there, sign in, and there's an exam. You'll click on it. You'll say it'll tell you, okay, now that you're starting the exam, you have this number of minutes. So it'll be an hour and 20 minutes, 80 minutes, unless you have some special accommodation. That'll tell you the right number then as well. You write the exam, and then you will learn your grade either immediately when you submit or within a day. Yeah, so someone says that in the open data structures book it mentions 2 log n plus 5. If you're a little bit more careful, you can count these things more, a little bit more carefully. It's the floors and ceilings here are not, I'm being sloppy with the floors and ceilings. You can't have this thing be equal to log n plus 1 and this thing start counting at 1. If this is equal to log n plus 1, then this starts at a half. But that's not really important. Yeah. Okay. Any more questions? For assignment 2, is add, remove, and min in amortized constant time acceptable? Yes. Add and remove in amortized constant time is acceptable. Min should be in constant time, no matter what. In fact, it doesn't really make sense to, it would be strange to get min in amortized constant time without it being in just worst case constant time. Yeah, so the exact transition around log n is not important. If you want to, you can probably even get the 6 down to a 4 here. But again, if you're comparing this to things that are taking billions of operations, whether you save 2 operations in this analysis is not so critical. And actually, these constants are really not important. More important is the 2 here, which you could make smaller. That's also an exercise in the book, but it requires using coins that are not fair coins. So it requires using coins that don't come up 1 with probability of half and 0 with probability of half. Does this course have a double pass rule? I don't even know what that means. Your grade is whatever grade you get according to the course grading scheme. So you do your assignments, you get some marks on those. You do your exams, you get some marks on those. They're combined using the formula that you get by looking at the course grading scheme. So I don't know, does that mean I care if you do pass all your assignments or pass your exams? I don't care. It's whatever the formula gives you. I care that you learn something. All right. No, I don't care if you pass the exam. Any information about the midterm next week? Yeah, just do the sample midterm, which is available on the course webpage. So I talked about this already. That's your prep. Think about the questions that are on there and questions that could be on a midterm that are just like those, and you can prepare as much as you want by making your own midterms that are similar to the one that's on the course webpage. That's your best bet. Okay. All right, so thanks for showing up again on a Friday afternoon. And so I won't see you in class on Wednesday because you'll all be writing the exam at that time. So I'll see you next Friday again.